Hello everyone.
Morning, sir.
Good morning. Okay, so you can listen right properly. Hello.
Yes, sir.
Okay. So 50 people. Where are the others? 140 registered. 49 now. Okay. Okay. So today is my first class, and yeah, rest of the semester I will teach. So first half was taught by Professor Susangdeep. I hope you enjoy it. And one person's email me for re-minor that I will take care. Just give us some time, then we will do that. And did you receive the grades? Graded copy? Graded copy?
Yes, sir.
Yes, sir.
Yes. Okay, good. We will take two quizzes. That I think next week after Dasara we will discuss with Professor Sasankdeep, and then one whatever Professor Sasank taught you, that we will take first, and then ours. That my part. Okay. So let me start. So I will present mostly by slide, and slides. Okay, let me share first. So if people are in home or hostel, where are you?
Some people are in hostel. Some people are on
Hostel
mobile.
also. Okay, some are in home. So you have option.
Yes, sir.
So can you see the slide? Is it okay?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay, good. Okay, so listen. So I will teach by slide. I will write less. Yeah, I am not comfortable to write in computer. Anyway, Blackboard is always better, always. But doesn't matter. So I will put all the information in the slide. Then I will share the slide end of the class or maybe next day. I think the same day I will do that to Moodle, and you download in the Moodle. Okay, I will do in the same day, probably on the same day at night or afternoon. Okay, so the first half, I hope you enjoyed whatever Host Sasandeep taught about the kinetics. Okay, so in CML 100, you learned about some thermodynamics. CML 103, this is the course mainly about the kinetics and its application. So whatever Professor Sasankdeep taught you, that is mostly kinetics with a lot of derivations. Am I right? Lot of equations, derivations, and from today in my half, I will focus more about its application part. Okay. So the first I will taught you some kind of kinetics as well as little bit of thermodynamics, how that will help to understand the mechanism of a reaction. So all of you are from chemical engineering. So in the chemical engineering people, okay, even whenever you will get a job in industry, okay, primarily I assume that you will go to industry, and you may divert to your field and join different industries or maybe IT. But since you are in chemical engineering, you have the background is chemical engineering as well as chemistry. So if you go to a join in a chemical company, then a lot of this is basically the lot of products are formed by the reactions, and how to optimize the reactions, how can you increase the efficiency of reactions, that you need to understand, you need to study the mechanism. And our course will help you to understand what is the reaction pathways, what is the mechanism, how to increase the efficiency of a reactions, especially if the reactions is driven by a catalyst. Okay, so today, from today, I will discuss mostly about this second half. We will focus mostly on its application part, and later in last probably like 6-7 lectures, I will give you an examples of different type of catalysis, how they are applied in industry, various type of catalysis, including some examples of the porous materials. So I will start first today that the first part whatever I will taught in my section is how to investigate the nature of a rate determining transition state. So from high school, let me get the pointer first. From your high school as well as from the lecture of Professor Sasangdev, so you are now familiar about the energy profile diagram. What is the energy reaction energy profile diagram? That is basically the Gibbs free energy or potential energy versus a reaction coordinate. Right, this you are very familiar from your high school. So you can see this is a two-step reactions. R is the reactant. This is converted to I. I is the intermediate, and there is a barrier. Right, barrier. So all the barrier is okay. So let's go that there is a barrier, and you know that this is a one transition state is there. So this barrier, all the reactant molecules need to overcome to pass the hill, need to overcome to get the next steps, and this is a two-step reactions. Then again there is another one step. You have to cross another one barrier to get the product. All right. So you can see that from your same high school knowledge or CML 100 that is a dot line from the R, this reactant. So anything below this dash line, basically below the starting material, that is the thermodynamic part, and above this is the barrier. So this is the kinetic part. Okay, so kinetic part. So kinetic and thermodynamics there is no relations. So this is the barrier is the part of the kinetics, and below the energy difference between the reactant and product, that may be exothermic or endothermic, that deals with the thermodynamics. So we will in this class, whatever the first part and second part, we will deal mostly about the kinetic part. That is a barrier that driven the efficiency of a reaction, or what is the rate of the reaction. Okay, how fast it is. So as you have seen here from this energy profile diagram, that there are two barriers, and they are on the top part, whatever the molecule will reside in this form, that is called transition state. Transition state. So on the top of the barrier, there are two transition state 1 and 2, and in the middle, this is called intermediate. There can be multiple intermediate, there can be no intermediate in a reactions. That depends what kind of reactions we are studying. So what is the difference between transition state and intermediate? Any idea? I'm asking you, what is the difference between transition state and intermediate? Can you tell anyone? Tell me.
Sir, intermediate can be isolated, whereas transition state is like an intermediate. It's like it cannot be isolated. It cannot
Why?
be obtained. Sir, because it occurs within the basically it is a concerted kind of a thing.
But this is a molecule. This is a molecule, not constant. That's I understand, but this is a molecule. Okay. Okay. Suppose two molecules are coming close to each other, but they are forming a single molecule in the transition state. You are close. You are correct. But why? You are telling the intermediate can be isolated, where the transition state cannot be isolated. That's fine. Absolutely correct.
Sir, it is not stable.
Okay. More precisely, why not stable?
It is high energy.
Okay, basically it's a very simple from the lifetime. Okay, the intermediate, it is like it is quite okay. Who are telling it is stable? It is more stable than transition state. Its intermediate has more lifetime. Its lifetime is much longer than transition state. That's the most simplest answer. To transition state, that's why it is called transition, right? This is a state of a molecule of reactants. Okay, this is a molecule. Doesn't matter, in a single systems, two molecules may come close to each other and form a single molecule, that is in the transition state, but this is a molecule. Okay, in another form of molecule. So its lifetime is very short. It's normally transition state lifetimes are around in femtosecond region, 10 to the power minus 15 second. Femtosecond. lifetime. In the very short time, it is impossible to isolate or to see the molecule what is going on. But intermediates, they are much longer lifetime. If the intermediate energy is lower than reactant, then you can isolate even. You can isolate. Suppose the intermediate is much lower than the reactant energy. Okay, but next step, the barrier is very high. Then intermediate, you can isolate. You can study. You can determine the structure. So that's why intermediates by spectroscopy, it is easy to see, not see, means you can determine the structure easily because it stays in longer time in that form. Okay, but transition states are very short-lived. That is the reason it is very difficult to get the structure of the or understand what is a transition state. And there is one spectroscopy, like in instrument method, that is called pump probe laser spectroscopy. That is basically femtosecond spectroscopy that can be used to know what is the nature of the transition state. And because of that, one scientist solely, his name is Ahmed Joel, American. Okay, he is Egyptian, but now he was American. He's a Caltech professor. He was the Caltech professor. He got Nobel Prize. I forget the year. I think that was approximately 15 years before. He got Nobel Prize. Okay, normally Nobel Prize is given to 3 people, right? This time 2 people got Nobel Prize, like last week. Most of the cases, scientists get Nobel Prize with 3 people. But Ahmed Joel is one of the few Nobel laureates. He got Nobel Prize in a single person. Okay, for to determine to develop a instrumental method to determine the structure of the transition state. His name is Ahmed Joel. Okay, so transition state is very important in any reactions because this resides on the top of the barrier, right? So you can see that if we just decrease the energy of the transition state, then definitely the barrier will be lower, right? So you can do that using a catalyst. That is very common, that you can decrease the barrier or decrease the energy of the transition state using a catalyst so that your reaction will be more faster. That is the reason why industry love catalyst. Most of the industrially used chemical reactions are catalyzed by a catalyst. Okay, because it accelerated the reaction rate. It increases the reaction rate by decreasing the barrier. So to understand what is the reaction pathway, how the reaction going on, and how to lower down the energy barrier, it is very important to know what is the structure or nature of the transition state. There is one way, as I told, by spectroscopic method. Okay, spectroscopy is, you cannot see, it is not like a microscope that you can see this. Okay, this is an indirect technique. But there are many other ways you can determine what is the transition state, nature of the transition state by experiment in laboratory. You can do that. You can understand what is the possible structure of the transition state, possible structure, by doing simple experiments in laboratory. That I'm going to tell you, that I'm going to teach you how to do that. Okay, and how it will be helpful to understand the pathway of a reaction. Not only for that, what is the how to modify the transition state so that you can lower down the energy, and it will be helpful in industrial processes. Then I will give more examples. Okay, so first part, I think about 7-8 lectures, I will tell you for different experimental techniques how to investigate the nature of the transition state, mostly by experimental techniques. Okay, that you can do in laboratory. We also do in our laboratory regularly. After that, I will also discuss some of the different type of catalysts, because catalyst help to decrease the barrier that you know from your high school. Okay, and that has direct application in industry. So industry uses a lot of acid-based catalyst. Industry use nucleophilic catalyst. This year's Nobel Prize has been given on nucleophilic catalyst. Okay, asymmetric organ catalyst. One of the prominent figure who got Nobel Prize this year last week is the David Macmillan in Princeton University in New Jersey, in US. Okay, so his catalyst is mostly nucleophilic catalysis. Here, the third one. In 2001 and 2005, 2 times people got Nobel Prize on metal catalysis. 2005 people got Nobel Prize on metathesis, and 2000 also on asymmetric catalysis like this year, but that is based on the metal catalyst, non-nucleophilic. So fourth one, if I have time, I will teach about the metal catalysis, mainly metathesis. But definitely I will teach the 5 part, that is the different kind of porous material and how to develop the catalyst based on the porous materials, because those are widely used in industry. One of the prominent porous material used in industry is zeolites. If you do any project in chemical science, I think more than 60% people are working on porous material, including zeolites. Okay, Professor Sridevi, I know, KK Pant, silica, zeolites. There are, I think most of the chemical engineering people are working on catalysis, and mostly most of their research are based on the porous materials. Okay, in chemical engineering, I'm not talking about chemistry. Okay, I am from chemistry, but you people are from chemical engineering. All right. Any questions?
No, sir.
Okay, okay. Yeah, just quick response. If you have any questions, please ask me. Okay, but I think every slide I will ask you that. Okay, questions. Okay, so I will encourage you to ask me questions. Whatever, it doesn't matter. The question is stupid or intelligent questions. It doesn't matter. Even if it's a stupid question, just ask me. Okay, that's done. Okay, 57 people only. Where are the other people? Just 1 second. All right. So, as I told before, the slides will be provided on the in the afternoon or evening of every class, and this is one of the book you can follow. Okay, we have in library, and I mean e-copies are there. I guess you can find, but there are multiple copies in library. This is the Dougherty's Modern Physical Organic Chemistry. Is one of the best chemistry book I have ever read. Okay, Dougherty, he is a professor in Caltech also. Okay, so it's a very nice book, and mostly I will teach from this book. But anyway, contents are here. So in that slide. Okay, so I hope that Professor Sasandip's class, you are quite familiar about the energy surfaces with a reaction coordinate, right? Energy profile diagram. So you are very much familiar with the 2D energy profile diagram like this. But what is this? This is actually a 2D. Okay, it is the simplest representative that you know from of an energy profile diagram from your high school. This is the Gibbs free energy or potential energy versus reaction coordinate. That we always tell, right? So this is a reactant. Suppose this is a reactant, then there is a barrier, then it comes the product. Use multiple steps, then it can go again like this one. Okay, so yeah, so you can see if it is multiple steps, then there will be multiple barrier, as we discussed in the first slide also. Okay, but this is just a line, curved line, right? If it is a higher energy, we tell this is the hill, our tungsten state resides on the top, reactant on the left hand side, and right hand side is the product. But in the reality, is it really the same? No. Actually, this energy profile diagram is it is a 2D. But this is just a cross sections of a 3D energy surfaces. So this is actually the energy surfaces of a reaction. You can see here, this is the hill. If you just follow my mouse cursor pointer, then there is a like a valley. You can think about that the valleys, you are putting reactant here. So reactant molecules in the valley. So this is lower in energy. Then on the valley in the reactant, you can see on this side there is a hill, just like a hilly surface, hill. Right. This side, so hill, this is the valley. Now there is a hill also here. If you want to go to the another one valley, suppose products resides in this valley, then you have to cross a hill. That is the barrier. But in the hill, you can see there is also these surfaces are higher in energy. This is also a higher in energy. So whatever the line drawn here, that is the 2D, just a line in the lowest energy surfaces. Okay. So how these 3D energy surfaces comes from where? From where we get it? There is not like a magic or we are drawing something. Okay, this is this A and B you are putting here and you just make a surfaces. This is the energy surfaces. So how do you know there is a hill here? How do you know this is a hill here? This is here. This is a nice 3D, nice picture of a hilly area. You have a hill here, you have a hill area, you have a valley here, right? What is that in a chemical reactions? This is the energy surfaces of a chemical reaction. But how do you get it? So how do you get it? So this is the answer. So when you are putting a reactant molecules from high school, you know that. So what happens? You are putting two chemicals together. They are composed of molecules. What happens? The first is collision theory. The molecules come to hit to each other because of the Brownian motion. When the two molecules come to each other, and some of the molecules they also get distorted, okay, because of the collision as well as kinetically, okay, with temperature. Some bonds they have vibrations also. Some bonds are getting longer, some bonds are getting shorter. During the collisions, some bonds can also break, right? So a lot of things happens when you are adding reactant. So once reactants are in a solution, suppose gas phase or solution phase, doesn't matter. Lot of things happens. First, during the Brownian motion, they move here and there. Their bond length, bond angle change. They collide. During the collision, they also get distorted. Right? This is normal. You know from your high school. They interact to each other. During the interactions, some of the bonds may break. They can also distort. They can also form a new bond also. When the new bond is formed, that also transforms to the product. So lot of things can happen. Lot of bond angle. Suppose you are using a methane. What is the bond angle? HCH 100 or 9 degree 28 minutes. Because of the movement of the Brownian motion or vibrations or collisions, bond angle may change. Even if it is a methane, it may be 109 degree 27 minutes, it may be 25 minutes, it may be 100 minutes, 108 minutes, it may be 100 some of the bonds may be of the methane might be 110 degree. So there is a infinite number of intermediates. Those are all intermediates. Maybe some of the intermediates are transition states also, but assuming all the transition states are intermediates as expected. Okay, so there are innumerable number or infinitive number of intermediates that are possible, right? And not only for that, every intermediate, because they are distinct from each other. Suppose a methane molecule, as I told, its bond angle, one of the molecule has one bond angle, hydrogen bond angle is 110. Another one is suppose 109. So definitely they have different structure which will associate with a different energy. Okay, so all the possible intermediates have different energy. Now if you plot a 3D plot with energy versus reaction coordinate, then definitely because of the different kind of possible intermediates, they will have different energies. Okay, suppose here the methane molecules has bond length is quite far. Okay, it may not be realistic, but it may possible. That's why you can see here the barrier is very high. So this is just like a dot 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 dot. Okay, it is a mapping. This is a mapping of energy of the all the possible intermediates as a function of their structures or reaction coordinates when a reaction goes on. Okay, so this is a mapping of energy in a 3D way. But how reaction will go? So definitely molecule will find the lowest energy pathway. So if we just draw a 2D line, just like one line, you can see this is the lowest energy, this is the lowest, then this is the lowest. And this hill, this is the lowest energy. If you go this way, this is the higher in energy, this way, this is the higher in energy. Okay, so this is the lowest barrier. Okay, where the transition state resides, where the transition state resides, is transition state resides here. So in 3D, this is a something like a flat area. Those are called saddle point. I hope Professor Sasangdev told you. Okay, this is called the saddle point in 3D. Saddle point. Okay, if you go this way, then energy will up, energy will go increase. If you go this way, energy will also increase. So this is the lowest energy barrier. It can go this way, it can also go this way, but these red lines are higher in energy. Whatever the brown original one is lowest in energy. That's why this reaction profile, energy profile diagram or reaction goes through the brown line. Okay, and this area, this is a 3D area. This is called the saddle point. Okay, and if you just take only these 2D lines, then you get this energy profile diagram that you know from your high school. Simplest drawing, right? Very easy to drawing. But this is not the actual case. This is just a cross section of a 3D energy surfaces of a reaction. Okay, is it clear? If it is not, I will repeat again. Is it clear?
Yes.
Okay, videos are here. Not videos, the recording. Okay, recording is going on. I guess recording is going on. Let me check.
Yes, sir. It is.
Yes, yes. Okay. Why it is showing bad network quality? Okay. Yeah, video. Okay. So I think recordings will automatically be saved, so you can also download the recording. Okay. So yeah.
Sir.
Yeah. Tell me. Yes.
What are these reaction coordinates? Is it sort of reaction progress or it's the distance parameter types?
This is the reaction progress. Reaction coordinates are, suppose you have here the starting material and it is a product. So this is the reaction product. Okay. So suppose you have A and you have product. So here then intermediates will be suppose A plus B. A can be distorted. So how A plus B is converting to the product? Okay, it is not like that is the instantly it will go. It is a slow process. Okay, so here all the intermediates, suppose here you have intermediate, here you have intermediate, this is the transition state, here you have intermediate. Okay, so different kind of intermediates. So I will go in the later with example. I will go with examples. Okay, all kind of intermediates. Suppose starting material you have suppose A, some of the bonds is getting elongated and reacting with B. Okay, suppose B is then it will give an intermediate. So that is actually progressing to form the product. Okay, clear? We'll give more examples. So reaction coordinate is the pathway that converts from starting material to the product. And y-axis is the energy. Potential energy. This is potential energy surfaces. Okay, and all are about the kinetics, kinetic barrier. We are not talking about the thermodynamics here. All right. Anything?
Yes.
Next questions, please. We'll come up more reaction coordinate later. Okay, you will see. Okay, so next is that. Okay, if you look at the previous slide, that I'm going to tell you that to investigate the nature of the rate determining transition state. So here is the two transition state 1, transition state 2. But as you know, I think from your high school, you know that which transition state is more important, 1 or 2? 2. Why? Well, this is associated with the highest barrier. So that you know from your high school, and that is called rate determining step. Suppose you are standing here, you want to go to product of this area, you have to cross 2 hills. Definitely you need to give more effort during the rock climbing, which has the highest barrier. So this is the lowest barrier. So this barrier you can easily climb and go to the intermediates, this valley. But the most challenging step is that step which is associated with the highest barrier, not higher, highest. Okay. So the transition state 2, that is deciding on a step which is associated with the most high barrier among all the steps in a particular reaction. So reaction rate is determined on that step which is associated with the highest barrier. That's why we tell this is called rate determining step. So we need to know what is the nature of that rate determining step. If you know, and if you suppose if you can change, if you can tune the transition state and lower it down, then definitely you can increase the rate of the reaction. You can engineer the reaction kinetics. You are engineering people. So we need to know what is the structure of the rate determining transition state, not transition state only. That is the rate determining transition state. That we will focus in our lecture in next 7-8 classes. Okay. So let me clarify here. So which is called rate determining step or rate determining transition state? Rate determining step that is associated with the highest barrier. Suppose the first one. This is similar to the first slide. This barrier is lower. This barrier is the higher. So your rate determining step is this step, right? Your rate determining transition state is here. What about here, the second one? Which is the rate determining step? First step or second step?
First.
First.
Are you sure? Okay, first step.
Yes.
It's quite obvious, right? So this is the rate determining step. Yeah. What about the third one? Here. Which step? First step or second step?
So second.
Second.
Make first.
So first.
I know that you will be confused. That's why I want to clear you.
First.
Some are telling first. What about others? Some people told second, right? So look at. I want to make sure it is clear. It is very common in chemistry and chemical engineering. Rate determining step. Let me clarify first, okay? And I will have more examples in the next slide. I told you the rate determining step is that step that involves the highest energy transition state. Okay, you can see here. It's commonly the chemical step that involves the highest energy transition state. Commonly. This is a very tricky word. That's why you're confused. That first step or second step. I'm telling you from the beginning that rate determining step is that step that is associated with the highest barrier. So first step R to Ri, this is associated with this barrier. the second step is associated with this barrier. Okay. So which is the highest barrier? Which one?
First.
First one. So look, suppose you are going a rock climbing. You are suppose you are climbing Everest. Your Everest is sitting here. E. Okay. Definitely there are a lot of base camp. Here is one base camp here, intermediate. So this barrier is the highest. Okay, first barrier. So if you reach the first barrier, then second step is not a big deal. Is it correct? To climb Everest? In reality, it is no. When you climb Everest, maybe first step, even though it may take longer time, but it will be easier because you have a lot of oxygen in the lower surface, lower altitude. Okay, and temperature. Maybe even though last step that has few more steps, but that is most risky. But in reaction, it is not like that the case. Right? It is not dependent on the oxygen level, or it is weather, or it is slippery, the path is slippery or not. For the reaction, is all are same. It is only looking at the barrier. So for reactions, if the molecule finds that they can climb up to the first step, then second step is very easy because you have less energy. Okay. So here the rate determining step is the first step. Okay. So you can see the transition state associated with the rate determining step is actually lower in energy compared to the highest energy transition state. So this is the rate determining step. Is clear? So rate determining step is associated with that step that is associated with the highest energy. So rate determining step or the transition state in the rate determining step may not be highest in energy. It is commonly highest in energy like 1 and 2 that we have seen from your high school mostly. If it is okay, if it is commonly seen as the highest, but not the actual case always. The third is the one of the example. Okay, so better to delete this word commonly. That you know from your high school. It is commonly the chemical step like number 1 and number 2 that involves the highest energy transition state, but this is actually wrong. That's what I'm telling you to clear your concept. So rate determining step is associated with that step that has the highest energy barrier. Okay. So one more example. Look at the third one, this slide and also the third energy profile diagram. You can see this is a complex multi-step reactions. Okay. You can see here reactant. This is one intermediate. Now you can see intermediates are lower in energy compared to the reactant. Here intermediates are lower in energy compared to the reactant. Here intermediates are lower in energy compared to reactant. Okay. So now there are multiple barriers. One of the barriers is here, but obviously this is lower. This is one of the barrier. This barrier is also low compared to these two assigned barrier. One is this, one is this. Okay, you can see this is the level transition state 5. 1, 2, 3, 4, but comparatively transition state 4 and 5 and 7 is the highest in energy, right? Not only for that, transition state 5 and transition state 7 is also associated with the step which have also very high energy barrier compared to other steps. So we are focusing on 5 and 7. Now look at which is the rate determining step. Rate determining step is that number 7 step, because this energy is higher in energy, total energy is higher compared to this energy in the number 5 step. Even though transition state 7 is lower in energy compared to the transition state 5. Okay. So in a multi-step reaction, the bottom line is the multi-step reaction, the reaction pathway involving the highest energy transition state is not necessarily the rate determining step. I want to make sure that this concept is clear to you. That's why I'm teaching here. This is a little bit of deviation from your high school. As I told, whatever you have learned from your high school, that commonly the highest energy transition state is the rate determining step, but this is not true. Okay, so the rate determining step, the transition state associated in the rate determining step is that step which has the highest in energy barrier. So transition state may not be highest in energy in the rate determining step. Is it clear?
Yes, sir.
Yes, sir.
So those people who told me that here that second step is rate determining step, now you please correct yourself. Okay, so this is wrong. Okay, so even though second transition state is higher in energy, but you see it is associated with a barrier which has lower in energy. It is not like a rock climbing or Everest climbing. That is different. Maybe your second step will be very challenging in real when you climb Everest or I don't know K2. Okay, the last step will be more riskier and more challenging. Okay, compared to the previous steps, because the pathway maybe it is very tough. Oxygen level is the lowest, right? Weather is the most, I mean the worst in the last step, but not the same thing in the reactions. Reactions will find only the energy barrier. Okay. Okay, any questions? Please no, then I will go. Okay, we have only 5 minutes. Oh, that's okay. I will go slowly. Okay, I will stop after this slide. Okay, so now let me tell you the next almost 5 to 7 lectures what I will teach. So we need to know. So now it is clear that what we are interested on, that is the transition state associated in the rate determining step. Okay, that is called rate determining step or rate limiting step. So we are interested on the only that transition state which lies on the rate determining step. Right. So we are interested to know the nature of the transition state of number 7. In suppose if we want to study these reactions, not the nature of the transition state 5. So we want this one. So we need to know what is the nature of the transition state in the rate limiting step, because that is associated with the highest barrier. So there are many experimental methods that we can use in laboratory, okay, to determine the rate determining step. One is order of the reaction. Why I am red color? Because you already know from your high school. Not only for that, you have, I don't know you have done or not, but last year I think you have not done any CMP 100 laboratory because of the COVID. But at least from Professor Sangdeep's course, you are expert, right? And you are very much knowledgeable about the order of the reaction, right? First order, second year, third order, yeah. So your order of the reactions, but order of the reactions can really tell what is the nature of the transition state. But this is the experiment, and transition state are very short-lived. There is no direct way to see the transition state. So you have to do multiple experiments to establish the nature of the transition state. Not one experiment cannot tell. Okay, one experiment cannot tell. So this is one of the first experiment you need to do to know the mechanism of a reactions, to know the order, to know the nature of the transition state. That is the order of the reactions. What is the rate law? What is the rate law? That you are very much familiar from the first half of CML 103. The second one that we will teach is the Hammond postulate. So what is postulate? Postulate is just like a postulate, means just like a proposed thing. This is not an experiment, but it is really helpful. a special case, but it's really helpful using a Hammett postulate for in a some kind of special reactions. So you can easily tell what might be going on in the transition rate determining step. Another one is that we can determine the activation parameters. This is very important. Chemist as well as, I mean, if you go any process Davies labs, KK Pants labs, okay, they always determine the activation parameters to understand what is the mechanism of a reaction. Okay, this is the experiment. Isotope effect. This is also another one vital experiments to understand what is the nature of the transition state. Study of the intermediate, as I told, there are many times intermediate you can isolate. Okay, and that also gives an hint that what is the reaction pathways it is going on, or maybe what kind of transition state is coming on after the next step up from the intermediate. Okay, and last one I will teach about the Hammett plot. This is very useful to understand the nature of the transition state as well as to understand the mechanism of a organic reaction. Hammett plot. Okay, so we'll discuss 1, 2, 3, 4, not 5 and 6. Okay, one by one. It will take probably 7 to 8 class minimum, or maybe more. Okay, with examples, and each experiments we will discuss a lot of examples, and I also give the problem sets and for practice. Okay, how those experiments will help and what type of experiment you need to do to determine the nature of the transition state in the rate determining step. All right. Okay, so I will stop here today, 11:50. Next time I think we should start sharp at 11. So please log in, okay, and join here by 11 o'clock every time. Not every time, means Monday and Wednesday is the 11 o'clock and Thursday is at 12 o'clock, right? Okay, so see you on day after tomorrow. And Thursday is I think holiday. So we will have one class on Saturday. Probably next Saturday we have class.
So I think Friday is holiday, right?
Friday is holiday, right?
Thursday, yes, no, Friday is holiday.
Friday is a holiday, Dasara. But you don't need to worry. We will have a makeup class always as per the
No, but our
IELTS.
CMA class is on a Thursday.
Thursday we have class. Oh, sorry. Yeah, we have class on Thursday. Sorry. Yeah. Friday we don't have class. Sorry. I had another class, so I was confused. Yeah. So we have 3 class today, Wednesday and Thursday. Okay. So okay. See you on Wednesday at 11 o'clock. If you have any questions, please ask. Okay, because this is the only one time we can meet. Any other time also we can meet by online. Okay, but after the class or during the class, if you have any questions, any doubt, any stupid questions, please ask. Okay, all time. Any questions? Okay, so slide I will upload on Wednesday. Okay, I didn't teach much. So Wednesday after class, I will upload the slide. Okay, all right. See you then. If you don't have any question.
Thank you, sir.
Okay, bye bye.
Thank you, sir.
Thank you.